In this video, I want to talk about resistors that are connected in series. So what does it mean when we say we have elements connected in series? So when just two elements connect at a single node, they are said to be connected in series. So let's just say we have two elements. For example, we have this resistor R1, and then we have this second resistor R2. So if you remember from before, each one of these you can consider to have two terminals. So we have terminal 1, terminal 2 for resistor 1, and also we have terminal 1 and terminal 2 for resistor 2. So when we connect, for example, these two terminals together, right? So even though there is a wire in between, right? Since there is no other component in the middle of them, we can consider these two to be exactly the same node. So if I want to just quickly redraw it, I can redraw it something like this, right? So the orientation does not matter. So we have R1, we have R2. So this is practically a single node. So let's just call this node A. These ones are not connected. So as you can see, these two components are both connected to this single node. And there is no other component that is connected to this node. That's an important point too. So when this happens, we say that these two components are in series. So what if I add this additional resistor like this? So let's just call this node B. So as you can see, we have R1 and R2 being in series because both of them are connected to node A without any other elements connected to node A. And we have the same situation for R2 and R3. Both of them are connected to node B, and there is no other element connected to node B. So as you can see, we can say R1 and R2 are in series, and also R2 and R3 are also in series. So that means that R1, R2 and R3 are all connected in series. So the same thing can be applied for any additional resistor too. So here you can see an example. We have this independent voltage source with the known voltage Vs here. We have the polarities, positive and negative side here. And then this one has two terminals, right? So we have node A, which is the point of contact between the positive side of Vs and R1, and there is no other component connected to node A. So that means that this voltage source and R1 are in series. Let's just take a look at the second node. We called it B. So at node B, we have two components that are connected, R1 and R2, and there is no additional component connected. So that means that R1 and R2 are also in series. So the same analogy can be applied to node C, node D, node E, node F, node G, and finally node H. So in general, we say that all of these components are connected in series. Why? Because for any node that we have in this circuit, there are only two components that are connected to that specific node. So now that we have this, let's just see what are the implications of having all these components being connected in series. So the first thing that I do, I assign some reference directions to these components, and I assign them kind of randomly. So for IS, I consider it from negative polarity to positive polarity in this direction. For R1, I call it from going from left to right. For R2, going from right to left, and so on and so forth. So I repeat this for all of them, right? But as you can see, there is no consistency between the directions that I assign to these currents, right? So R1 and R2, they are connected in series. But for R1, the current that I assume is going from left to right, while for R2, it's going from right to left, right? So at this point, this does not matter. So what it matters is when we want to apply Kirchhoff's current laws and voltage law. So that's when it is important for us to write those equations considering the direction of the currents in each of the elements. So what we can do is that we can write KCL for each one of these individual nodes that we have in this circuit. So let's just do it for node A. For node A, if you remember, KCL was stating that the algebraic sum of all the currents that enter or exit a node equals 0. So here, since we only have two currents either entering or exiting this node, we can easily write the KCL. So as you can see here, we have IS to be entering the node. So we consider it with the negative sign, so we have negative IS. And we have I1 to be leaving the node. So we consider it with the positive sign. So we have I1. So let me just erase this. So we have negative IS plus I1 equals 0. So based on this simple equation, we can conclude that IS equals I1, right? Because negative IS plus I1 equals 0. So that's one of the conclusions that we have. So let's just repeat this for node B. For node B, we have I1 entering the node. I consider it with negative sign, so we have negative I1. We have I2 also entering the node. So we have negative I2 equals 0. The conclusion from this equation is that I1 equals negative I2. So let's just repeat this for node C as well. For node C, we have I2 exiting the node. So we consider it with a positive sign, so we have positive I2. We also have I3 exiting the node, which means that we consider it with a positive sign, equals 0. What is the conclusion from this equation? I2 equals negative I3. And we will do the same for the rest of the nodes. So we do it for node D, we do it for node E, we do it for node F, G, and finally H. So as you can see, for each one of these nodes, since we only had two currents, it was very easy to come up to a conclusion. But what is that conclusion? The conclusion is that series connected circuit elements carry the same current. So let's just do this again for node A. So we have node A. If I write the KCL, we have negative IS plus I1 equals 0, which concluded that IS equals I1. So that means that the direction that we assigned for IS and I1, they match, right? So we said that IS is going from the negative side of the voltage source to its positive side, and we said that the current that goes through R1 goes from its left side to the right side. So as you can see, the path is basically continuous. However, for node B, the conclusion was that I1 equals negative I2. So as you can see here, I1 is basically going from the left side to the right side, but the assignment that we did for the direction of I2 was from the right side to the left side. So as you can see, they are basically coming toward each other, right? But based on the KCL, we concluded that I1 equals negative I2. So that means that if we want to have everything consistent, the true direction of I2 should be the same as I1. So this is the conclusion, right? And you can repeat that for all of them as well. So the final conclusion is that if you have elements that are connected in series, the current that goes through them is going to be all equal. So when we do this for all the nodes, this is the conclusion that we come to. We have IS to be equal to I1. It is equal to negative I2. It is equal to I3, equal to I4, negative I5, I6, and finally I7. So this is the conclusion that we get by applying KCL for these components that are connected in series. So now that we have this, what is left for us is to find the value for IS. And if we know the value for IS, we practically know the value for the rest of the currents that we have for these elements. And then when we know the currents for all the elements, we can use simply the Ohm's law to find the voltage for each one of these resistors individually. So to get the current, what we can do is that we can use KVL. So we write the KVL around this single closed loop or closed path that we have. So I follow the passive sign convention. You remember when we set for the passive sign convention, when we have the direction of the current going in the opposite direction of the voltage drop. So for this voltage source, the voltage drop happens from the top side to the bottom side. But the current goes from the bottom side to the top side. So it goes in the opposite direction of the voltage drop. In that case, we consider the voltage to be negative. Another way that I mentioned was that if the current goes through the negative side of the voltage source, we consider it the negative, with a negative sign. So this is the first term that we have when we go through this closed path. Then we get to R1, following the passive sign convention. We assign the voltage here. So to make everything consistent, we consider for all the resistors that the current goes in the direction of the voltage drop. So if we do that, there is no need to use a negative sign for the Ohm's law. So for this one, we have IS multiplied by R1 with a positive sign. So this is the voltage across R1. And again, you see that I use IS. I don't use I1 anymore because IS equals I1. I do the same for resistor R2 as well. So since IS goes through this, now I consider the voltage to be in this direction, right? So the voltage associated with this resistor is IS multiplied by R2. For R3, we do the same. So we have V3 in this direction. So this voltage equals IS multiplied by R3. And then we do it for R4, R5, R6, and R7 until we get to the point or the node where we started the closed path. So if we do this, as you can see in this equation, we have Is to be common in a lot of the terms, right? So what we do is that we just manipulate this equation a little bit. So we have the voltage source in one side, and on the other side we have all the current and the resistors. So when we do this and when we factor out Is, what we see is that Vs, the voltage of the voltage source, equals Is, the current that this voltage source is providing, multiplied by the summation of all these resistors that are connected in series. So this is an important conclusion. And it all drives because we prove that when components are connected in series, the current that goes through them are exactly the same. So this means that all of the 7 resistors can be replaced with an equivalent resistor to find Is. So this equivalent resistor, I call it R subscript EQ, equals the summation of all the resistors that are connected in series. So Req equals R1 plus R2 plus R3 plus R4 plus R5 plus R6 plus R7. And then based on that, I rewrite the equation Vs equals Is multiplied by the equivalent resistor, or Req. So generally speaking, if we have k resistors, so k can be any number, but if we have k resistors that are all connected in series, so that's important, right? If they are all connected in series, first of all, the current that goes through them is going to be equal for all of them. Second of all, the equivalent resistance equals the sum of all the resistances, all the k resistances. So we have Req to be equal to, this is the summation sign, the summation of all our i's for I changing from 1 to k. So that means that it doesn't matter how many resistors are connected in series. The equivalent resistance is the sum of all the resistors. So in another word, if we say, let's say we have this box in which we have several resistors that are connected in series inside of it, but we only have access to these 2 terminals, right? So we don't know what is inside. So for all intentions and purposes, we can use the equivalent resistance like this, that is calculated by this equation, and the rest of the circuit won't be affected, right? So these 2 boxes are completely equivalent for the rest of the circuit, whatever is like connected on this side, right? From this side's eyes, these 2 terminals behave exactly the same way, whether they are 7 resistors that are connected in series or one single resistor in which the value is basically the sum of all the resistors that are connected in series. So in this video, we saw how we can connect resistors in series, what are the implications, what we can do using KCL to prove that the currents that go through elements that are connected in series are exactly the same. And then finally we saw how we can find the equivalent resistance of a bunch of resistors that are all connected in series.